CO2, one molecule here will do 289 times more global warming than carbon dioxide. Because of the way lower concentration, it still only contributes about to 1/5 of what carbon dioxide does. Now, where does all this carbon dioxide come from? Most of it comes from energy production. With industrial processes these days, they take a lot of energy, and well, we all know that a smartphone these days won't even last one day on its battery. So, to put the carbon dioxide emissions into some perspective, here are, well, some lists per hour of what we make carbon dioxide wise. What we breathe basically does nothing. But even planes are nothing compared to what one coal-fired power plant produces in a single hour. One coal-fired power plant produces so much in 1 hour, in fact, that our tutor, Francesco, can go to his home in Tuscany and back to Groningen, not but 800 times before he produces as much carbon dioxide as one coal-fired plant does in 1 hour.
Okay. Now that we have identified the problem in the sources, the question is, carbon dioxide? In fact, we can. There are three major approaches to do it. First is fuel combustion. The idea is that instead of burning coal in air, you separate the oil you really want in the combustion. After that, the combustion is in a pure oxygen environment, resulting in an exhaust gas largely of carbon dioxide and water vapor, which is easy to separate. One of the benefits of this is that there are very high capture rates, actually over 98%. Nevertheless, an expensive air separation plant is required, and it is difficult to be implemented as a retrofit option for existing installations. Then we have pre-combustion capture, in which the capture takes place prior to combustion. With this method, you first turn coal into a gas. This gas is called synthesis gas, and typically consists of carbon monoxide and hydrogen. Then, the carbon monoxide reacts with steam, releasing carbon dioxide and additional hydrogen. They are easily separated, so they are separated and the hydrogen can then be used as a fuel. However, the fuel conversions required are relatively complex, making pre-combustion capture more suitable for use in nuclear power plants. Finally, we have post-combustion capture, in which you just basically burn coal in air. What this means is that you run the power plant as normal, and after the combustion, there is a chemical separation process that recovers carbon dioxide from the exhaust fumes. Post-combustion capture can be retrofitted to existing power plants or be used in new industrial operations. However, the high need for steam to recover carbon dioxide can significantly reduce the generating capacity of the power plant. Now let's recap. We have oxy-fuel combustion with very high capture rates, but it's an expensive process and it's not available for existing power plants. We have pre-combustion capture with easy separation of carbon dioxide, but the complex fuel conversion steps make it more suitable for use in nuclear power stations. And finally, we have post-combustion capture, which can be retrofitted to existing power plants. But the high need for steam to recover carbon dioxide can significantly reduce the generating capacity of the power plant. Now, to one degree or another, we have experience with all of these methods. Currently, post-combustion capture would be the most suitable one because it can be retrofitted to all existing power plants. Hence, I've chosen to focus on this.
So, in general, there are four main approaches for the separation of carbon dioxide from other stream gases. The choice of the most suitable technology depends on the characteristics of the gas stream, which may depend on the power plant technology. The applications of cryogenic separation, selective membranes, and adsorption solids are economic for streams which have high concentration of carbon dioxide and high pressure, typically produced by pre- and oxy-fuel combustion processes. Now, for dilute flue gas streams with low concentration of carbon dioxide and low pressure, typically produced by plants which use the post-combustion approach, the best existing capture method is absorption using a chemical solvent. Given the reactive nature of absorption, amine-based solvents are well suited to capturing carbon dioxide from these streams. This technology is applicable to the majority of the existing fixed point sources of carbon dioxide, and it is envisaged that they could be retrofitted with relativities at the back end of a given coal-fired power station. Now, let's focus on the molecular level. What's going on there? Primary and secondary react with carbon dioxide, forming carbamate species. There are two proposed mechanisms for this reaction. The first proposes that carbon dioxide forms a bond with the hydrated amine group, giving a deuterium in the first step. The second step, the protonation of the amine takes place of a base molecule. Now, please pay attention to this base molecule because we will come back to it in a while. The second mechanism proposes that these deuterium species are very unstable. These intermediates are likely transition states. The bonding between carbon dioxide, the amine, and the proton transfer takes place at the same time. So, this mechanism is conservative. Now, as you can see, both mechanisms form carbamates, whose degree of hydrolysis is temperature dependent. So, during the absorption process, we keep the temperature low, and the reaction proceeds from right to the left. During the generation of the solvent, the temperature is raised, and the reaction proceeds from left to the right, releasing a stream of carbon dioxide and allowing the solvent to be recycled. Now, tertiary amines. Tertiary amines cannot react directly with carbon dioxide because they lack a free proton. Now, what's the proposed mechanism for tertiary amines? When CO2 is hydrated, it gives a proton and a bicarbonate. Tertiary amines act as Lewis bases, binding this proton and drive the hydration of carbon dioxide to the right. Now, during the regeneration of the solvent, the temperature is raised, the reaction is reversed, and finally a stream of carbon dioxide is at the disorber column. Now, what choices do we have in terms of solvent selection? You can see the chemical solvents that are used currently for acid gas treatment. For example, monoethylamine offers the highest removal capacity, but due to its low volume, there are high losses because of evaporation. Diethylamine has the same removal capacity and the same reactivity as glycolamine, but with lower evaporation losses. Also, as you can see here, cheaper. Now, for tertiary amines, methyl diethylamine and triethylamine are not used as the other compounds, but as bases in this. These mixed systems take advantage of the unique properties of the amine solution. In fact, they can also as the basis which deprotonates the primary of the second amine, as we saw before. Now, the choice of the most suitable amine solution or blend is not a walk in the park. We have to take into consideration the removal capacity, their boiling point, their degree of degradation when oxygen and other corrosive compounds are present in the flue gas stream, and finally, of course, their
Now, these degrading cost money because you lose your amines. They also can be very toxic and corrosive. Corrosive means that you damage the inside of your plant through, well, damaging the piping and stuff. However, the products formed, some of them, there are nitrosamines and nitramines. Nitrosamines are carcinogenic, meaning they cause cancer, and nitramines are expected to, but they're not sure. They degrade quickly in safer, less harmful molecules in nature, so that's not really a problem. Now, the industrial process itself, the way is quite simple. Your exhaust gas, instead of just being pumped into the air, go through the absorption column, where clean amine, which means there's almost no carbon dioxide in the amine yet, is sprayed on top, which reacts with the carbon dioxide and at the bottom, the amines which have reacted, so with lots of carbon dioxide in it, are pumped away to the generation column. The regeneration column, again, from the top comes the carbon dioxide rich amine in this case, which is then heated through reflux, which is what this reboiler and condenser are for, quite simple. The amine are condensed again and flow back down with no in it anymore, which can be sent back to the absorption column, whereas on the other side you have a stream of pure carbon dioxide gas. As a whole, this process looks like this, with a nice little heat exchanger in the center. Your amine needs to be cold to capture as much carbon dioxide as possible, and it needs to be heated anyway because the carbon dioxide needs to leave from the rich amine stream. So it's just a nice little bit of efficiency there. The plant itself would then look like this, with power being generated here, exhaust streams through there, and regeneration here.
Okay, so now we have captured the carbon dioxide and it must be transported and stored in a suitable location. Several options have been suggested. Storage in geologic formations, like here, and especially in depleted oil and gas reservoirs, represents the best near-term option. Another option is the oceans, which have by far the largest potential capacity for the storage of captured carbon dioxide. So as you can see, the storage of captured carbon dioxide is possible. The problem is that the planet may only be able to store up to 100 years of all human-created emissions. Since we probably live longer than that, storage is thus a temporary solution. As a result, the reuse of CO2 is extremely important. Enhanced oil recovery operations have already been used for decades, facilitating the extraction of oil that would otherwise be too costly or impossible to recover. Also, science has now known that it's possible to use carbon dioxide and hydrogen to make hydrocarbon fuels, though large amounts of energy. Now, you may think that reuse solves the problem, right? Actually, this is not the case, at least not yet. This is because the emitted carbon dioxide is calculated to be much more than what can be reused right now. So the problem basically still exists. If we want to say that we have truly solved the problem, the reuse methods still need to be improved.
So, to recap, we've looked at where carbon dioxide comes from, in this case mostly fuel combustion and in power plants. Now there's three different ways to which you can go to capture this. Oxy-fuel combustion, post-combustion capture and pre-combustion capture. And we've had a little look at post-combustion capture and how this is done these days with amine solvents, which leaves you with pure carbon dioxide gas. This pure carbon dioxide gas is then either stored or reused, but until we start reusing carbon dioxide more than that we use it, the concentration of carbon dioxide in the atmosphere is still going to rise. So basically, we still have a problem.